Next, let's talk about the dualization technique. The dualization technique is very simple. It is to simply apply a base splitting method to the corresponding dual problem. And this is possible because certain primal problems that have constraints have corresponding dual problems without constraints. And we've actually seen an instance of this dualization technique before. We have seen it when we derived the method of multipliers. In the setup of method of multipliers, there was a primal problem, a primal minimization problem with a linear equality constraint. We took the dual of the primal problem, and the dual problem is an unconstrained problem. And when we applied the proximal point method to the dual problem, we obtained the method of multipliers. Let's use the dualization technique to obtain an alternate derivation of ADMM. Again, let's consider this primal dual problem pair. But now in this setup, we'll refer to this dual function, f star composed with minus a transpose, as f tilde, and then we'll refer to this function as g tilde. This primal dual problem pair is generated by exactly the same Lagrangian, and what we will do is we'll consider this dual problem, define this as f tilde, define this as g tilde, and then apply the FPI with DRS, where we apply the proximal operator with respect to g tilde first. In this case, we'll refer to the DRS iterates as the psi iterates. So we have the DRS mapping, the FPI, maps from psi k to psi k plus 1. And we'll refer to the output of the resolvent as mu k plus 1/2 and mu k plus 1. Again, as a minor technicality, in this setup, we will use the scaling parameter of the resolvent as alpha, which is different from what we had before. In the previous derivation of ADMM, when we used the IPC technique to derive ADMM, we used the scaling parameter 1 over alpha instead of alpha. To transform the DRS FPI into a more favorable form, we will be using two identities that we had established before. One is that if we consider the resolvent with respect to the operator A with t added to it, then the resolvent can be evaluated using the resolvent with respect to A, but with the inputs shifted in this manner. And then the second identity is that to evaluate the proximal operator with respect to the function f star composed with a transpose, we can solve this minimization problem and then perform this update. So to transform the proximal operator with respect to g tilde, we utilize both identities to get this. And then to transform the proximal operator with respect to f tilde, we just use this identity to get this. Then the psi k plus 1 update was defined as psi k plus mu k plus 1 minus mu k plus 1/2. But instead of having the mu k plus 1 here and the mu k plus 1/2 here, we can just substitute this in, and the result is this update. Now the updates of this iteration no longer explicitly depend on mu k plus 1 and mu k plus 1/2, so these two lines can simply be removed from this 5-line description of the algorithm. That way we get a 3-line description of the algorithm. And then these terms can be collected into a form that more resembles the augmented Lagrangian. So when we do that, we get this 3-line description of the algorithm. Now, in the next step, we perform the substitution where we define uk as psi k minus alpha times ax tilde k. So with that change of variables, the algorithm further simplifies into this form. Now note that the order of the update is y, x, u, but here the u update relies on x tilde k rather than x tilde k plus 1, and the xk plus 1 update relies on uk plus 1, which is to be computed in the subsequent line. So again, we have this exact same reordering and relabeling issue. So we define xk plus 1 as x tilde k, yk as y tilde k, and then we perform that change of variables, and then we reorder the updates, and then we cut the iteration so that the updates come in the order of x, y, and then u, rather than y, u, and then x. Then we get the same algorithm as before. Okay, so now we've arrived at the same exact algorithm ADMM. So, and if total duality holds, the regularity condition that we had stated holds. If alpha is positive, then uk converges to u star, a dual solution, axk converges to ax star, and byk converges to by star. Now here's the reasoning of the convergence analysis. So this is the same algorithm as before, and when we did the analysis with starting from the IPC technique, then that allowed to establish that AXK converges to AX star and BYK converges to BY star. In the DRS FPI, we know that the mu k plus 1/2 iterates converge to the dual solution mu star because we are applying the DRS to the dual problem. And we established that a mu k plus 1/2 has this relationship with psi k, and in the previous analysis starting from IPC, we know that BYK converges to BY star. So putting this on the left, we have psi k converges to the limit of this, mu star minus alpha times by star minus c. But y star and x star, those represent primal solutions. So since ax star plus by star is equal to c, we are substituting that in. This is equal to u star minus alpha times ax star. And then the uk iterate was defined as psi k minus alpha times ax tilde k. So since this converges to ax star and psi k converges to this, we get that the limit is mu star. Oh, let me correct a sign error here. So here, this should be a plus. Okay, so for ADMM, we saw two derivations, one based on the IPC technique and the other based on the dualization technique. And let me briefly remark on this. So for some methods, we present multiple derivations. So ADMM is not the only method for which we will provide multiple derivations. PDHG will be a method that we provide 3 derivations for. One with as a variable metric ppm, another derivation as using the BCV technique, and another derivation based on the linearized ADMM. We will talk about the method PDHG and these 3 separate derivations in depth soon. These different derivations, they provide related but distinct interpretations to the single algorithm, and therefore they are all useful in a complementary way. And furthermore, the different derivations show intimate connection between the various primal dual methods. The next algorithm that we will derive using the dualization technique is the alternating minimization algorithm, often abbreviated to AMA. Frankly speaking, the name is not a very good name as it is too generic, but the name alternating minimization algorithm is what the author of the algorithm wrote in the paper, so it is what it is. So we again considered the same problem form that we had considered for ADMM. We minimize f of x plus g of y subject to the same linear equality constraint ax plus by equals c, and we have the same dual problem structure. We'll refer to this first function as f tilde of u and the second function as g tilde of u. This primal dual problem pair is again generated by the same Lagrangian, and we'll assume the same regularity conditions as before. The difference, though, is that in this case, we will assume that the function f is mu strongly convex, and this implies that the dual function f tilde is smooth, and it is smooth with this particular smoothness parameter. Okay, then to derive the AMA algorithm, we simply apply forward backward splitting to the dual. Specifically, we perform the fixed point iteration with this fixed point encoding. And remember, the strong convexity assumption on f implies smoothness on f tilde, so we are able to perform this gradient update for the function f tilde. The algorithm, just written in abstract, becomes this. And then to transform this iteration into a more favorable form, we use the identities that we had restated in page 18, and also this identity for the purpose of evaluating the gradient of f tilde. So this tells us that if we have the function f star composed with a transpose, we take the subdifferential of that, and then evaluate that at y. We can obtain the a subgradient, or the gradient in this case, by solving this minimization problem, and then performing and obtaining u as a times x. So using these identities and carrying out some calculations, simplifying things, we can write out our forward backward splitting update in this manner. In this form of the algorithm, we have the iterate uk plus 1/2, but we eliminate uk plus 1/2 by taking its form and plugging it into this instance and this instance, and then carrying out a few other steps of calculations. we're able to express the AMA algorithm in this three-line form. Now, note that the difference between AMA and ADMM is that in the first step, we are minimizing the Lagrangian rather than the augmented Lagrangian. In the second step, we are minimizing the augmented Lagrangian. In contrast, in ADMM, we were minimizing the augmented Lagrangian in both steps. Here, I write the argument with respect to x of the regular Lagrangian, not the augmented one, and then I use the equality notation in the definition of xk plus 1, and that is because we assumed that the function f is strongly convex, so the minimizer is guaranteed to be unique. On the other hand, for the function g, we made no further assumption beyond that the function is CCP and that it satisfies the regularity condition. So the argument y is guaranteed to exist due to the regularity condition, but there's no guarantee of y being unique. So that's why we are using the inclusion notation, defining the iterate yk plus 1. The dual variable update, the UK variable update, is for AMA, has exactly the same form as that of ADMM. So this method is, again, referred to as the alternating minimization algorithm, AMA, and it's also referred to as the dual proximal gradient. The reasoning behind this name is quite clear because even though once we perform some transformations and rewrite things, we can express the algorithm as performing an alternating minimization of the Lagrangian and the augmented Lagrangian, but at the same time, we were able to derive this algorithm as applying the proximal gradient method, the forward backward splitting, to the dual problem. So it is quite natural to refer to this method as the dual proximal gradient method. I consider this name to be the more descriptive and therefore better name. In any case, if total duality holds, the regularity condition holds, and the function f is indeed mu strongly convex, and the parameter alpha stays within the step size range, then the dual iterates converge, the UK converge, and the primal iterates xk converge, and then byk converges to by star. Note that here in the primal iterate convergence, the yk is guaranteed to converge to y star, and the byk is guaranteed to converge to by star, but we have no direct guarantee on the yk iterates themselves. And in the case of ADMM, we also had an analogous set of guarantees where we had convergence guarantees on AXK and BYK, but we did not have direct guarantees on X and Y themselves. And the reason that is in some sense expected is because the X iterates and the Y iterates are defined as argmins. So since we have the argmin, when the solution is not unique, the specific choice of yk plus 1 will depend on how we choose among the many minimizers. And when that's the case, it's not reasonable to expect that the y iterates themselves to converge. But once we multiply b to the yk iterates, then we do expect that matrix vector product to converge to by star. However, in the setup of AMA, the x iterate is uniquely defined through the argument due to the strong convexity assumption. So in this case, we can expect the xk iterates to converge to the xk iterates themselves to converge to x star. The high-level message that I want to convey is that the AMA algorithm is an instance of the forward-backward splitting fixed-point iteration. So if we assume a condition on the step size so that the underlying FBS iteration converges, then the AMA algorithm also converges. However, even after this type of high-level argument has been made, in order to carefully establish these type of convergence claims, one does have to go through the bookkeeping carefully. So here's the bookkeeping that leads to the convergence results for the AMA algorithm. So under the stated assumptions, the underlying forward-backward splitting fixed-point iteration converges, and specifically that implies that the dual iterates UK converges to a dual solution U star. Then after that, since we had assumed total duality, there exists a saddle point for the Lagrangian L, which we write as x star, y star, u star. Since x star, y star, u star is a saddle point of L, in particular, x star is an argument of the Lagrangian with respect to the minimization of x, where y star and u star has been plugged in. The optimality condition of this x star means that 0 is in partial f x star plus a transpose u star. We get this differential equation simply by taking the subgradient of L with respect to L and plugging in x star into that expression. And then we put A transpose U star on the left-hand side minus A transpose U star on the left-hand side, and then apply the inverse of partial F. But in this case, F is assumed to be strongly convex, which means F star is L smooth. So instead of writing partial F star, we can just write gradient F star. So X star is gradient F star minus composed with minus A transpose U star. Then in the next step, we recognize that the definition of xk plus 1 can be written as grad of f star minus A transpose uk. In the algorithmic description, we define xk plus 1. We wrote xk plus 1 as the arg min of the Lagrangian. But if we actually write out the optimality conditions, we can alternatively express xk plus 1 in this way. Then f star is a smooth function, which means the grad of f star is a Lipschitz continuous, and in particular continuous function. So the fact that uk converges to u star implies that, since this is a continuous mapping, xk converges to x star. So this gives our primal iterate convergence for the xk iterates. Next, in our final step, our uk iterates converge to u star. So that means that the difference between the subsequent u iterates that converges to u star, that converges to 0. But this difference is equal to this difference. But since axk plus 1 converges to ax star, and here we have c, so byk plus 1, that needs to converge to by star, so that in the limit, the linear equality constraint is satisfied. So this gives us the convergence result for the yk iterates.